time we're going to look at a dual cavity antenna. This has poor ultra-wideband performance, at least from a group delay perspective. There's a cavity on top, a cavity on the bottom, and you can't really see it, but there's a feed right here that is connecting the top conductor down to the middle conductor. If we look at the impedance versus frequency, in this case, we're looking at 5 to 6 gigahertz as the operational bandwidth. And this is kind of like a good or a typical impedance that you would see for this type of antenna. And, the corresponding S parameters look good as well. You'll notice there is a lot of variation though in the impedance, and also when we then look at the radiation pattern from 5 to 5.5 to 6 gigahertz, that radiation pattern moves around quite a bit as well. So thinking about the first antenna, the impedance didn't have this level of variability, and the far zone patterns were very stable. This antenna moves around quite a bit, and in that case, the group delay is significantly worse, right? We're looking at 2 to 8 nanoseconds of variation. So this would not be a good antenna design from an antenna group delay perspective. If we then move on to a second metric, which is an antenna fidelity factor. This is similar to group delay in that it's a metric of how much distortion is introduced. But in this case, we're looking at an input signal traveling through the device, and then we're looking at the output signal, and we're using a cross correlation to figure out how much correlation there is between the input signal and the output signal. So if we consider the black waveform here to be the input signal, we look at the red signal as being the output signal. And as we move the signal across, like right now, there's no correlation. That there's no overlap. But as we move that signal across, well, then we start to see, there's some correlation there. And as we continue to move the signal farther, we can get another correlation metric. And in this case, we're about reaching peak correlation, or the maximum correlation between the two signals. And then, we continue moving it on until there's no correlation again. Oh, I also wanted to mention here that, we have to factor in or normalize the received signal magnitude. As it propagates, the output signal is going to be significantly weaker than the input signal. And so we need to account for that as part of this cross correlation calculation. But given that kind of methodology, we can go back and look at the WD6000. The green is the input signal, the red is the output signal. If we look at the autocorrelation on the input signal, so basically, the input signal correlated with itself, we're going to see a correlation of 1. The signal is identical, that's what we would expect. And the displacement here is 0, just meaning that whenever the signal is overlapped exactly on top of itself, well, then the correlation is 1. Same thing with the output autocorrelation, we're getting 1 with the displacement of 0. This is just kind of like a sanity check to make sure that at least the algorithm that we're using, or the implementation of the algorithm is working. So then whenever we plug in the cross correlation and look at the output signal correlated to the input signal, we're seeing 0.99. So again, very good correlation for this WD6000 antenna, and the displacement is off, which just means that we had to move this output signal down roughly a quarter nanosecond in order to get it to line up. Moving on and looking at it with the packaging, we'll get a little bit more variability here in the time domain signal of the red one. You can see some more ripples towards the end, and the cross correlation has dropped a little bit to 0.989. So again, still very good. And then whenever we look at the dual cavity antenna, clearly the output signal in this case is significantly different, and the cross correlation has dropped to 0.7